Okay, so we're missing a little school here, so I just want to go through the homework assignment. So 29, this is an exothermic reaction because of the negative delta H. It's a negative 67 kilojoules, so that means it's releasing heat and it is exothermic. Number 30, we have this reaction here, and we have 275 grams of sulfur. We just want to make sure we get that to moles, and a mole is 32 grams. And so we can calculate that, although I don't have a calculator here. 275 divided by 32, we get 8.6 moles of sulfur. And then according to the balanced equation here, negative 296 kilojoules per mole, and there is just 1 mole, so kind of be careful of that. Look at the balanced equation, and it is 1 mole, so 296 kilojoules. So then what we're going to do is say times 296, we're going to get negative 2,544 kilojoules of energy released. So that's for part A. Part B for number 30 is 7,400 kilojoules, and for C, 693 kilojoules. But make sure that you are showing your work for those. And for C, 693 kilojoules. Okay, and those are all negative, so just make sure that that's heat released. And it's negative. All right, 31. I mean, if you put the negative number, it says, or you can say it's released. So number 31 is negative 252 kilojoules, and then number 63, we have A. And that is negative 1,652 kilojoules. For B, again, show your work. 826 kilojoules released, or I'll put a negative. For C, let's see, negative 7.39 kilojoules. And for D, which is a limiting reactant problem, negative 34.4 kilojoules. So you'll have to do a limiting reactant here to find out which one is the limiting reactant and use that one. And I don't seem to have the solution worked out here, so you'll just have to kind of wait till you get back if you want me to do that. But you're going to take 10 grams of iron, get that to moles, 2 grams of oxygen, get that to moles, decide which one from a 4 to 3 ratio, which one's going to run out first, and use that one to figure out how much heat. Okay, treat heat like a product. All right, the next thing that you're going to need to do for the climate change part of this is just to read through this or listen to me talk about it, and we'll take a short quiz on it in class. We're just going to talk about the science behind it. Really not interested in talking about the politics, because I just feel like this should not be a political issue. This is just the science of it. What we want to do about it, that's maybe a political question, what we do about it, but this is just the science of it. So greenhouse gases are carbon dioxide and methane. Now carbon dioxide is a huge, it's produced a lot. Every time you burn a fossil fuel, we get carbon dioxide. So we have a ton of this. Methane is actually a more potent greenhouse gas, meaning it holds in heat better, but we don't have as much of that. However, there is a permafrost in the Arctic that they're just desperately afraid that if that melts, it's going to release so much methane and it'll just escalate the whole climate change. We are increasing the average temperature of the Earth. It's probably hard to believe, like we're in a school cancellation right now because it's so cold. But right now Australia is heating up to levels that are not sustainable for life over there, and a lot of animals and stuff are dying. In 1958, the amount of carbon dioxide has been measured since then at a volcano in Hawaii. And the amounts are just going up and up and up. So Okay, the pre-industrial concentration of carbon dioxide was 280 parts per million, and I'll show you a chart later that it never, for the most part, went above that. And last, or 2 years ago, December, 404.93 parts per million. A year ago, 405, and last November, 408. So we're just climbing, climbing, climbing. And it's higher than any time in the last 650,000 years. And our temperature is increasing faster than ever before. The 4 hottest years on record were the past 4 years. And we're likely to see that. And, like, well, okay, it's getting hotter. We obviously are a big contributor. China is the biggest contributor. And that's because we consume what we need, and we just consume a lot and we burn a lot of carbon dioxide. The average sea level is expected to rise 1 to 6 feet. If it rises that much, we will lose much of the coastline that we have come to enjoy with the beaches and that kind of stuff. So that's just convenience for us, but, well, there's a lot of money to be lost, but small islands will disappear. In 1910, Glacier National Park had 150 glaciers, and that number has shrunk to 25 as of a couple years ago, and in the next, not really sure how long, but fairly soon, expected to lose all of the glaciers. We're looking at plant extinction, animal extinction because of the change in climate. A couple of things that contribute to it: rainforest destruction. Anytime we cut down trees, they store a bunch of carbon dioxide and they're releasing it. They're no longer able to take it away from the atmosphere, so the more trees, the better. Some of the impacts: coral bleaching has impacted much of the world's coral reefs, and that, of course, is sea life destruction as well. Sources. There are so many sources. When people deny that climate change is happening and it's happening because of humans, they're not reading enough, or they're being obtuse about it. The science behind it is solid. And you're always going to find 1 or 2 crackpots that will cite this, that, or the other thing. But when you have 98% of any PhD scientist saying, no, this is really happening, you need to go with that. So just a little bit more about the science behind it. The CO2 concentration in past eras, what happens is they take cores, ice cores, and they analyze the air bubbles trapped at various depths dating back to 650,000 years ago. And what they found is that values since about 1800 have skyrocketed, and that's when we started to burn the fossil fuels. Again, the concentration was hovering right around 300 parts per million, but ever since the Industrial Revolution, we're just growing and growing and growing, putting us around 600 parts per million by 2050 if we don't do anything about it. And you can see from the next few charts that since 1800, the global average temperatures have drastically increased. So you can look at these temperature anomalies, and we can talk a little bit more about that in class, but look at what happened in 1800. And you could look before that, and it's remained unchanged for 650,000 years. But you'll notice from the 1800s to now what's happening. This is a really interesting chart in that you see for centuries this atmospheric carbon dioxide hovering right around here, and there's been some drops and like that. And you'll hear people argue that there have been ice ages in the past and temperature fluctuations in the past, and there have. But if you look at the data from this is the past 650,000 years, and now you're looking at 1950s when, your grandparents were teenagers, and you look at what's happening here to the current level, we're just spiking like never before. All right, there is a little bit more to the specifics of science, how scientists actually do this. There are a couple of isotopes of oxygen, oxygen 16 and 18, and you recall we studied that. It's the number of neutrons, the difference in the number of neutrons in the nucleus. Oxygen 16 is lighter, of course, less neutrons, and 18 is heavier, and water contains both of these isotopes. And they use the fact that O16 is lighter and therefore evaporates more quickly, and O18 is heavier and condenses more readily. So as air rises from the equator to the poles, it cools and the water condenses out, and O18 goes first and leaving more O16 in the air. In colder times, even the equator is cold and more of the O18 condenses out at lower and lower altitudes. By the time the air reaches the North Pole, much of the O18 is gone, leaving primarily O16. And scientists measure the levels of O16 and compare it to current ocean levels of the isotope and determine the relative temperatures during that era. And so this right here, you're missing, sorry, the Y part right here. This is oxygen 18 isotope levels versus the temperature. So I could write that in there. O18 levels. Okay. And you can see what's happening again over the years since 1800-ish. Okay, so kind of explaining what's going on here, the O18 decreases with temperature, and this graph shows the differences in O18 concentration and annual precipitation compared to the average annual temperature at each site. The higher the O18 in the polar ice, the warmer the temperature. The coldest sites, location like Antarctica and Greenland, have about 5% less O18 than ocean water. The ocean water levels of the isotope come from measurements in the calcite shells deposited through the years. So as O18 condenses out of precipitation into the ocean, the water travels from the equator to the poles. The colder it is, the more O18 condenses out, leaving the O16 behind. The less O18 found at the poles and ice, more in the ocean, means overall colder global temperatures and vice versa. So, to summarize all of this, we're living in a very scary time. I've heard it said many times that this is the tipping point. If we can stop it now, we have a chance. If we don't, the prospects of our planet are dire. So I'll leave it at that, and hopefully you'll do a little bit more research and you'll think about this for your future and your children's future.